today we are very happy to have Fernando Martin here. And the reason that he is in Stockholm is actually that he is becoming honorary doctor in Stockholm. He is actually become it already, perhaps, because this was decided already 2020. But due to the pandemic, this ceremony where you officially get this status is this week. So that's why we have the opportunity to have this colloquium here. And Fernando, I just say a few short things. He got his PhD in Madrid in the University Autonoma in 1986. And then he has been to many places, to Bordeaux, to Paris, and to Chicago. And finally he came back to his alma mater and is since many years now professor there, and he has a really big group. And he works with many types of interaction between particles and light and atomic or quantum systems, I should say. Both collisions with heavy particles and with photons, and how they interact with atoms, with molecules, with clusters, which he has done a lot together with Henning Zettergren here in our department, and also with surfaces. And later years he has worked a lot with the rather new field of attosecond physics. So you can make very short light pulses, so it's so short that you can dream of, at least think of, that you can time how the electrons moves, because electrons, they move on the time scale of attosecond, or a few hundred attoseconds. And this is a growing field, started with looking at ionization from atoms, but Fernando has much bigger ambitions and want to do this with molecules and understand chemistry, sort of the electron dynamic, how it influences chemical reactions. So welcome, Fernando. We look forward to your talk.
Well, thank you very much, Eva, for the nice introduction, and I'm very happy to be here once again. Last time I came here, I realized, talking to my colleagues yesterday, it was 19 years ago. I used to come rather often in the past, but then suddenly, for different reasons, I didn't come back. Probably because I moved to a field that is not so close to what most people are doing here. And but in any case, I'm extremely happy to be here and to see you in person after so long. Okay, so today's talk will be about attosecond science applied to problems of chemical interest. Well, the way I have organized this presentation is by assuming that I was going to have a very diverse audience with very different backgrounds in physics, also at different levels of their scientific career, from, let's say, a master student or undergraduate student to full professor, experienced professor. So this means that, well, the talk will have necessarily parts that will be extremely boring for some of you, because you know that already. Others will find it interesting, and the other way around. So there will be, for sure, parts that everybody will recognize very easily. But I hope that at the end of the talk, there will be a part, at least, that will be of interest for all of you. So I will start by introducing very elementary notions that I think are important to understand where we are playing here. So it's about time scales, and well, here you see the time scales that look normal to us, at least the first two or maybe the third one. Things that happen in these time scales. Now, you start reducing the size of the systems that you are interested in, then well, for instance, you can find processes that occur in the nanosecond time scale, and this is for instance protein denaturalization. Protein folding occurs typically there, but this is not chemistry. The time scales in chemistry are much shorter. And so chemistry is about forming and breaking bonds So typically these bonds break in the picosecond time scale. But molecules also vibrate. You know, they have bonds, but these bonds are not fixed. They vibrate, and the typical vibration times are of the order of femtoseconds. And you also have electrons, and the electrons are very fast, as Deva told you already in the introduction, extremely fast. And this is a very simple exercise that you can do. You can take Bohr's model, so nothing complicated, and take the formulas and calculate the time an electron takes to orbit around a proton in the hydrogen atom. And you will find that this takes around 150 attoseconds. So that means that if you take in mind, you keep in mind that chemistry is about breaking and forming bonds, but these break up and formation of bonds is entirely driven by the way electrons move. That means that if you are able to follow electronic motion in real time and eventually to control it, then you can modify chemistry and do a new chemistry. And this is basically, well, the concepts we have been playing with in the last few years. Just to give you a more, you know, intuitive idea of the time scale we are interested in is here you see the relation between an attosecond and a second, and between a second and the age of the universe, and you have the same ratio. So that means that from the point of view of any electron, a second is infinite time, basically. And not only a second, but even in microsecond is infinite time. So this is where the time scales and the orders of magnitude of what we are doing. And just hopefully, well, we are happy that we don't use attoseconds to measure times of what we are doing in daily life, because otherwise my talk would take 2.7 to the 21 attoseconds, okay, which is about 45 minutes, which is the time I would like to talk to you. So the very first thing you want to do in order to see electrons in real motion of electrons in real time is to make a movie. So I will tell you how movies are done. So you know this already. So a movie is about taking pictures of an object in motion at different times. Okay, and then to produce different frames that you project one after the other one. And when you see this in the screen, you get the impression of motion. Okay, this is a movie. Now, to make a movie, there are two important concepts here. One is that for how long you take the picture that corresponds to a single frame. Okay, so for instance, you want to take a picture of an object moving down the slope, like this little car here. So you can you can choose a shutter speed of one part in 400 seconds, which means that you take this image only for this very short time. Now, if you use a longer exposure time, then the object will appear fuzzy, simply because the object moved during you were taking the picture. And of course, you take an even longer time, then you even don't see the object. So a very important point is that if you want to record the motion of an object, the time during which you have to take the picture has to be much shorter than the typical time the object takes to move significantly. Okay? This is the importance of shutter speed. The other important concept is that the time between consecutive frames cannot be too long, because if it is too long, then you miss part of the motion. So this has to have also the necessary time resolution. And in fact, this is what you want to record, for instance, the motion of a water drop, falling into a pond. Then, of course, you have to take a lot of pictures consecutively in order to catch the details of this motion. And well, at the beginning of this, I think you could see, in this particular case, there were like 5,000 frames per second, which is a lot. It's a lot of frames in a very short time interval. But of course, this is not enough. You work in the attosecond time scale. So one of the main problems is to have a tool that is able to do these things in the attosecond time scale. Now, but there is something else. So, attochemistry, as I said, is about making movies of this electronic motion and eventually to modify this electronic motion in order to do some new chemistry. And so the goal is to see electrons in motion. But there is a problem. And the problem is that if you were able to record this motion, you wouldn't see this. You should see something that looks more weird, simply because we have Heisenberg uncertainty principle, and we cannot follow the trajectory of any electron, okay? So the picture, even if we have the time resolution, should be fuzzy. But this is not a problem of how we record the picture. Is because nature is like this. So the picture will be fuzzy. Okay, so which are the tools that we have nowadays to access the time scale and to produce these movies? Well, there are basically two kinds of tools. One is tabletop lasers that generate attosecond pulses in the extreme ultraviolet and the soft X-ray regime, and which typically have low intensities. And the other one are pulses generated in accelerator-based free electron lasers, which generate X-ray pulses. And the difference with the previous case is that the intensities are much, much higher. So these two tools are now able to deliver light pulses with a duration of few attoseconds, typically tens and hundreds of attoseconds. So, and the question is how to use these tools in order to make the movies in the way that I showed you. Let me, before going there, for those who are not familiar with this, I think since there are also students in the audience, I think it's good just to say a few words about how these pulses are produced, because this is technologically is complicated, and but I think it's very interesting. So, in the case of free electron lasers, basically what you need is an electron accelerator of several kilometers, which like the one that we have in Hamburg in the European XFEL. So in this accelerator, basically what you have electrons that go through a very long tunnel, as you have seen in the previous picture, and they are accelerated until they reach velocities that approach the velocity of light. And when they leave the accelerator, they enter what is called an undulator. So an undulator is a sequence of magnets of inverted polarity, so that when the electron goes inside this undulator, it starts oscillating, and because of these oscillations, it generates light, synchrotron radiation light, but it is generated in the form of a pulse. And this is because the spacing between the undulators is between the different magnets is designed in such a way that there is a coherence in the light that is emitted at different times, and then you generate a pulse. The other method to generate attosecond pulses is based on what is called high harmonic generation, and I will explain very briefly what it is. And so high harmonic generation, basically what you need is an intense infrared field, very intense, okay? So, and then use it to shine an atom. So here, this is a cartoon of what the potential that an electron would see in an atom, so the nucleus should be around here, okay? And then the electron should be confined to move into this well. Now, this is the potential that the electron could see if there was no intense laser around. Now, when you switch on an intense laser, like this one, infrared, with a period of 1.5 femtoseconds, so this is an infrared pulse, so you have an electric field that looks like this one. You know, you have a frequency, but you have some envelope here that defines the duration of the pulse. And of course, you want to calculate the potential that the electron experiences in the presence of such a pulse. Well, this is a trivial thing. You integrate this over the differential of x, and then this is the potential you get. So you see that this potential oscillates with a frequency omega, and is multiplied by E0. And E0 is the amplitude of the electric field, and this amplitude, the square of this amplitude, is related to the intensity of the light. So if the intensity is very high, this E0 is going to be very high, and then Vx of t is going to be very high, very large. As large as to overcome the potential that the electron feels in the presence of the nucleus. So that means that when you add this potential to the atomic potential, and you see how it changes in time, you will see that it oscillates in time with the frequency omega, and you will see something like that. So what you see here in red is just a cycle of this pulse, just one cycle. So it changes sign, And you see that then you have a potential that has a slope here. The slope comes from this part of the potential. You have x here. So, and this can be positive or negative depending on the sign of the sinus function. So what happens? The slope can be as large as you want. If E0 is very, very large, this slope will be very large. And so what will happen is that the electron at some point can escape. And what happens when the electron escapes? And this is a more elaborated cartoon in which you can see this potential now in 3 dimensions. And then you see that when the slope is big enough, you see an electron escaping. It is accelerated because it rolls down the slope. And then when you change the sign of the slope, then the electron comes back. It comes back, and the most frequent situation is that the electron comes back, but it goes away. But sometimes the electron comes back to the initial position it had. And when this happens, since this electron has a lot of energy, it can recombine with the nucleus, but to do that, it has to liberate all the energy it has acquired. And the only way to liberate it is by emitting light. And this light is emitted, so think that a period of this oscillation is just 1.5 femtoseconds, as I told you. So this light is only emitted at the instant of recombination. So it has to be, the time during which this light is emitted is much shorter than the 1.5 femtoseconds. So it is of the order of attoseconds. So it is precisely this light that is represented here in the form of some flashes that, that is generated in the process of high harmonic generation. And this is an attosecond light pulse. Okay, so at the end, what you get is the parent infrared light that you use, very, very intense. And superimposed to every half cycle, you have a little attosecond pulse. And the frequency of this of the light contained in this attosecond pulse lies in the extreme ultraviolet, usually, okay? Because the electron accumulates so much kinetic energy in the round trip that this energy corresponds to being in the extreme ultraviolet. So then what people do is they separate these little attosecond pulses from the main infrared pulse, and then you have your attosecond pulses to do whatever you want with them. So how to use these pulses? Now we have something that has the necessary time resolution, and we know how these pulses can be produced. So there are different ways to perform, to record the movies. These are, I would say, the most frequent ones. There are not so many so far, but these are the ones that have been used more extensively. The first one consists in performing what is called an attosecond X-ray pump, attosecond X-ray probe. So basically it consists in shining the system with an attosecond pulse, and then let the system evolve, and then take a picture with a second pulse at different times. So what people do is, okay, they shine with a pulse, and then they come with a second pulse and take a picture at a given time. And then they repeat the experiment, and then they take the picture later. And then they go on this way. So they get a sequence of frames. And we know that these frames have the necessary time resolution to avoid being fuzzy, because we are taking these pictures with attosecond pulses. Okay? And the other thing is that the delay between the two pulses, the separation between the different frames, must be of the order of attoseconds too. And this is guaranteed by the fact that these pulses have the right duration, and so experimentally you can control the delay delta t between them with attosecond resolution. The other approach, which was the first one that was used, is not very different. It's different in the sense that the pulse that was used to probe the system, to take the pictures at different times, it's an infrared, a few femtosecond infrared pulse. And the reason is that, as you have seen, in the process of high harmonic generation, you are using an infrared pulse to generate the attosecond pulse. And so since the infrared pulse was already there, well, they reduced it, let's say, okay, by lowering the intensity, because you don't want to burn your system with a very intense infrared pulse. So, but lowering the intensity of a laser is not a problem, okay? So this can be done routinely in the laboratory. And so this is the first scheme that was used. So I want to emphasize that in any of these two schemes, the interaction between any of those pulses with an atom or molecule or any material is very weak, because the intensity of these pulses is very, very weak. The process of high harmonic generation is very inefficient. Very few events lead to the recombination of the electron. Most events lead to the ionization, so the electron departs and goes away forever. It doesn't come back. So it's a very inefficient process, so you have very few photons arising from this process. So this is a very weak intensity, what you have. The same about free electron lasers. You have many more photons in a free electron laser, as we have seen. The intensity is much higher. But still, we are in a regime where we can consider that the interaction is very weak, as you will see later. And the same here, because by lowering the intensity of this, you guarantee that you belong to this weak intensity regime. Okay, this is important because in this way you avoid distorting too much the potential of the system. Therefore, you can investigate the intrinsic electron dynamics of the system, not the one you generate with your pulses. In other words, when you make a movie, you don't want your camera to destroy the object you want to record. Okay, so that's the reason why you need low intensities. So this idea of pump probe is not original from attosecond science. It was introduced by Ahmed Zewail, who won the Nobel Prize because of this, in which, well, he was using in those days pulses of infrared, of femtosecond duration, which was the technology that was available in those days, but the idea of just pumping the system, inducing some dynamics, and then taking pictures of these dynamics at different times was introduced by him. The difference is that the time resolution that they could achieve in those days was of the order of hundreds of femtoseconds. So the only motion they could follow with this technique was nuclear motion, which, as I told you before, occurs in the femtosecond time scale. So, the interaction of attosecond pulses with atoms or molecules has some special characteristics. The first one is that the light is produced in the extreme ultraviolet and X-ray wavelength regions. So that means that with absorbing one of these photons, you ionize any atom, any molecule, any solid. So you always have ionization. First thing. Second thing. These pulses, as I told you, interact very weakly with the system, so they don't distort the potential. And well, this you could understand qualitatively from what I said before, but I mean, there are formulas that allow you to check that this is really the case, and this is the famous Keldysh formula that tells you that whenever this gamma, which is the ratio, you have here the frequency, here you have the ionization potential, and you have here the intensity, then this has to be much larger than 1. If this is much larger than 1, then you are in the weak field regime. And this is the case even for free electron lasers. Because for free electron lasers, as I said, there are 8 orders of magnitude more intensity than for pulses generated through high harmonic generation. But it doesn't matter, because omega here is huge. It's X-rays. So, it's a huge frequency. So this is always larger than 1. And the other thing that is extremely important is that these pulses have a very short duration of the other attoseconds. And that means that, qualitatively speaking, that means you have a big uncertainty in time, a very small uncertainty in time, because you measure time with a lot of precision. But this translates in a large uncertainty in terms of energy. And that means that, in fact, what you have in your attosecond pulse are photons of very different energies. And this you can understand it better with some cartoons. So you have monochromatic light. Of course, you will have a wave like this, and then there will be only one frequency. So the light would contain only one color. But you have a very short pulse, like this one, for instance. This one has a duration of about 1 femtosecond, so it's even longer than the ones I am interested in. Well, and you take the Fourier transform of this, which is the right way to calculate these things. then you realize that the frequencies of light that are contained in these balls, of course, have a peak around a given frequency, but the width of this distribution is as large as several tens of electron volts, which is a lot. It is much larger. I mean, and this is 1 femtosecond pulse, and you reduce by a factor of 2 this, which is something you can do currently nowadays, then this would double the width. So you would have typically 20 electron volts, 30 electron volts of difference between the low energy photons and the high energy photons you have in your pulse. And this is much larger than the energy separation between the electronic levels of any molecule. And that is important to consider. So the message is it contains many colors, but really many. Okay? So what happens when you shine one of those pulses in a molecule? Here, well, these are the energy levels of a molecule. This is phenylalanine molecule, I think. And these are the different energy levels. So the ionization potential is around 9 electron volts here. And this is a typical spectrum of one of these attosecond pulses. So you see the bandwidth of the order of 20 electron volts, as I told you. And within 20 electron volts, you have all these energy levels. Okay? So when you ionize this, and you have the energy to ionize from any of these energy levels, then what can happen is that you can absorb photons of low energy, for instance, from one of these energy levels close to the ionization threshold. And so you absorb a photon of low energy, produce a photoelectron here with a given kinetic energy, but at the same time, you can ionize your system from an inner orbital by using a photon with much higher energy, such that at the end, the photoelectron that is produced has exactly the same kinetic energy. So you perform an experiment in which you detect electrons only, and you want to know from where the electron came from, you wouldn't know. It could come from any of these levels. So what does it mean? This means that you have a coherent superposition of electronic states. You produce a coherent superposition of electronic states in your cation, and there are coefficients there that are given by the ionization amplitudes. So this is an electronic wave packet. So you produce an electronic wave packet. So in this sense, it's not what happens with monochromatic light, in which you absorb a photon of a given frequency, and then you know exactly what is the kinetic energy of the electron that will produce. This is what happens, for instance, if you use synchrotron radiation. So then the bandwidth is almost zero. It's very small. In any case, much smaller than the energy separation between the energy levels. Therefore, if you absorb a photon of this frequency, then of course you will produce electrons, this energy, but if you absorb it from here, because this is the only frequency you have, you will produce an electron of different energy. So if you measure the energy of your electrons, you know exactly where the electron came from, okay? So this is not the case with attosecond pulses. So let's go back to making movies. So how do we make these movies? So I will concentrate now on this pump probe scheme that I introduced. So XUV attosecond pump, infrared femtosecond probe. So I will show you the first movie ever produced in a molecule, not in an atom, in a molecule. This was produced in 2010. This is the movie. Okay, not very nice. You probably you understand nothing. That's normal. So I will now expand and show it in the way, the different frames, one after the other one, okay? So these are the different frames, here you have the different frames. Still, you don't understand anything. Okay, just for curiosity, I always do this parallelism. This is the first movie ever produced of electronic motion in real time in a molecule, which is comparable to the Lumiere's movie of the train coming to the station. And well, when I read these things, so when people were watching this movie for the first time, people ran away from the room because they were afraid that the train was going to hit them. But I didn't see you running away when I showed you the attosecond movie. Why? Why you didn't run away? Well, you didn't run away because you need some special devices to understand the movie. You need glasses. So you go to a movie theater in 3D, you need glasses in order to understand what you are seeing. Now, if you are not wearing glasses, then of course you don't understand that the movie is about dinosaurs, running maybe somewhere. And if you don't wear glasses, then you are tempted to say that you would see here are dinosaurs, but they are not, okay? So, and how the glasses must be? Well, theory provides the glasses. So, in this field, more than in other fields, you need theoretical interpretation, theoretical modeling. Otherwise, the movies are there. The proof that something happens is there, but you don't understand anything. This is the situation nowadays. Maybe in 10 years, theoreticians will not be useful anymore, okay? But as up to date, they are needed. So, what is the theory we use? Well, you have seen in what I said that we need quantum mechanics, because I'm talking about coherent superpositions, electronic wave packets. So forget about classical mechanics. We have seen that, we have electrons. I didn't say that when you ionize a molecule, the remaining cation can also break in different fragments. This does not happen in an atom. You don't induce a nuclear reaction, by shining an atom with an attosecond pulse, okay? But you can break a molecule with an attosecond pulse, okay? In addition to ionize it. So that means that you have correlated motion of electrons and nuclei. And you have to take into account this. And you have to investigate this in the time domain. So no stationary picture anymore. So the only way to do it is by solving this equation. So this equation is extremely difficult to solve. I will not say any detail. This morning I had a nice seminar, introductory seminar with students, where I told them some hints about the theory, but I think in this audience probably it's not necessary. We try to do it the best we can. And I will show you the lab where we do it. And this is not a joke. This is a real supercomputer center. And when you open the door, this is what you have inside. And this is what the supercomputer center we are using to perform our calculations in order to solve this Schrödinger equation I showed you, okay? Okay, and this is our more modest computer. I had to show it. This is the attosecond computer we bought a few years ago in Madrid. That is obsolete nowadays, and it's going to be replaced by the tomato machine that you will hear about later. Okay, so now I will give you, in the remaining time, some examples, very few, of how these things were done. So this is the paper in which this movie I showed you at the beginning was recorded. This was a movie about electronic motion in the H2 plus molecular ion, the simplest molecule that you can find in nature. And it was done by using this pan-probe scheme I mentioned. And this is what they measured. These are the heads of the dinosaurs, remember the movie? These are the heads of the dinosaur. And this is what the theory, produced by solving this complicated equation. But the important thing here is that you see here some oscillation of colors. That means change of sign of some observable. But what the theory was able to say that this change of colors in these time intervals is representing the jumping of the electron from one nucleus to the other one as a function of time. So what this movie is telling us is that they are, the experiment is able to follow the motion of an electron in a covalent bond, in time. And then they see how the electron moves from one side of the molecule to the other one. And this was the first time that this was observed in real time. Of course, no surprise in the result. We knew that already. Okay? We know in a covalent bond, the electrons are shared by the two nuclei. But this is the real proof that this is indeed the case. And then, well, there were more applications. The former one was H2+, then there were some works on helium. Helium is also a very simple system. And then experimentalists were able to reconstruct the two-electron wave packet in helium, with the help of theory, of course. And without going into too many details, they were even able of recording the birth of the electronic wave packet. Not only how the wave packet evolves in time, but also how it is created. And well, here you see how it is created. Well, look at this. It does from nothing. Then there develops some structure here. This was in the vicinity of a first back resonance in helium. And well, I can play again the movie, and then you see how it builds up in time, and it builds up very, very quickly. Okay, so this is the proof that the technology is working. It allows us to see electronic motion in real time. Then, but hydrogen, H2+, and helium is not really very interesting for chemistry. So if we want to do some chemistry, we should try these tools in real stuff for chemists. And well, then there was an experiment performed in Milano by the group of Mauro Nisoli on phenylalanine, which is already a decent molecule, okay, let's say. And the technique was exactly the same, PAM-PROF by using an infrared probe. And well, basically in the experiment what they do, they shine phenylalanine. This is, by the way, the spectrum of the attosecond pulse that is not as nice as the one I showed you that was, had a beautiful Gaussian envelope. This is just a theoretical pulse that we produce. This is a real one, which more ugly, you know, spectrum, but still, you know, the bandwidth is around 20 electron volts, as I told you. So then you ionize phenylalanine and you produce a coherent superposition of all these states. Okay, so you have an electronic wave packet, and then you generate some motion that occurs in the attosecond timescale. And then they came with a second pulse, the prof pulse, and this prof pulse takes a picture. Now, but the picture is complicated when you have a molecule like this one. And it's complicated because of the, you know, the small energy spacing between all these energy levels. You know, this second pulse further ionizes the molecule, leading to a decation. And a decation is quite unstable and breaks. And so what the experiment, and it breaks not in the attosecond time scale, but as I said at the, in one of the first slides, in picoseconds. And then what the experimentalists record is the fragmentation yield as a function of the delay between the two pulses. And of course, if you don't have attosecond resolution, you should see something extremely boring like this. This is something that is standard in femtochemistry. But if you are able to scan a region with attosecond resolution, then you see that this is not just a smooth background, you have oscillations. And these oscillations have a period typically lying between 2 and 4 femtoseconds. And these 2-4 femtoseconds is too short to be due to any nuclear motion. It has to be the signature of electron motion. So this was the first experimental evidence that there was some electron dynamics that could be observed. And so the important point is that these oscillations reflect what happened here at the very beginning. But remember that to get this, you had to go all the way until you produce the decation, you break it. So that's why the signature of these electron dynamics is so faint, you know? Because a lot of things happened in between. You produced this motion and you recorded it. And this is the actual electronic wave packet. This is the result of a calculation, okay? So, but you see that the electron density changes sign as a function of time. And the interesting thing from the point of view of chemistry, you are a chemist or you have some notions of chemistry. In phenylalanine there are amino groups, carboxyl groups, and all of them are, have a particular electron affinity. And what you can see is that the sign, the color, for instance, around the amino group changes from purple to yellow and the other way around. And it does it periodically. And so that means that the amino group sometimes like having more electrons that it would like to have in general, or it has the right number of excess charge, okay? But this is absolutely counterintuitive for chemistry, because in chemistry is kind of average over long times. But at the short time scale, the basic concepts of chemistry do not hold anymore. And I think this was a very interesting discovery. So what you can do is just to fix, see what happens around one of these functional groups, And then you can record the oscillations here as a function of time, so you integrate over this volume, and you see that these are oscillations. You take a Fourier transform, resolving time, and then you get that there are two typical frequencies, two characteristic frequencies of this motion here. And you see when these frequencies show up in time. And then you can compare these when you perform the same Fourier transform in the experiment. And well, you can see that the interesting thing is that there are only few frequencies showing up, okay? And they show up more or less at the same times. Not these ones, of course, because here the theory can say nothing, because this is the region where the pump and the probe pulses overlap. So we cannot say anything about that. So the interesting point here is this was a proof that what was observed here was indeed due to the reminiscence of the electronic motion that was induced by the pump pulse at the very beginning. And of course, this, I forgot to say, although it's written here, that these calculations performed in 2014, well, didn't include any nuclear motion because it was very hard to do for such a large molecule. And we didn't include the probe pulse, etc., etc. But more recent calculations in which the nuclear motion has been included, not for phenylalanine, but for a larger molecule, tryptophan, well, shows similar behavior. So this picture is not destroyed. And here you can see a comparison between these frequencies that are calculated from this electronic wave packet and those that are measured experimentally by recording the ion yields as a function of the pump probe delay. Okay, so there have been more studies after that using basically the same tool, this same pump probe tool, but I'd like to say a few words about new directions, how this field is evolving. Because using an infrared probe pulse to take pictures is not the best thing you can do. First, because since it is infrared, photon energy is small, so sometimes you absorb more than one photon. This complicates the analysis. It also induces nuclear motion, and the duration of the infrared pulse, as you saw, is not of attosecond duration, is a few femtoseconds. So this is not the optimum conditions, but these were the optimum conditions to perform experiments at the beginning. So in this respect, I think it's interesting to read a review by our chair here. Probably she forgot she wrote this, but it's there, where precisely she discusses some new directions, okay? Okay, let me, then, one direction. One direction is to use these attosecond pulses to control nuclear dynamics. This means that if you control nuclear dynamics, you control the way molecules break. Then you control the chemistry of the molecules. And this is a theoretical adventure in a smaller molecule, of course, glycine, okay? If we want to include nuclear motion, you have to reduce the size of the molecule. And then these are just two different attosecond pulses, okay? And then, well, forget about these two figures here, are very complicated. But the interesting point is that depending on the pulse you use, here you have glycine, you can favor the breakup of the molecule here by breaking the carbon-nitrogen bond, or you can favor the breakup of the carbon-carbon bond. And this is just by designing attosecond pulses in a different way. And, well, the explanation takes some time, but I think an important point is that these attosecond pulses indeed can be used to control the way nuclei break. And remember, nuclei follow the orders of electrons. So electrons dictate all the time how nuclei should move. And because we are acting on the electronic motion, we are able to tell the nuclei to do this or that. I think that's the important message here. Another direction is to perform these attosecond pump, attosecond probe with two attosecond pulses. These are currently done, currently means now, at 3 electron lasers. And this is easy to say, but it has some problems, and I will mention only one here. These pulses are nice, intense, etc., but they have a little problem in that they change from shot to shot. And this is because the way these pulses are produced in the free electron lasers. So it was a little adventurous to perform these experiments, but before doing this, then theoretically we simulated the effect that using pulses that change from shot to shot would have in the dynamics. And there are good news. There are good news because, you know, since the pulses are so short, here what you see, these are different pulses. These are the envelopes of the spectra of different pulses produced in a real free electron laser. Okay, and when you use all of them, because they are so short, they don't have much effect on the dynamics. So you don't blur it. And what you see here is the dispersion, these shaded areas in green and in blue and green and red. This shows the dispersion of your charge dynamics when you use this set of different pulses. By the way, these are 100 pulses we use for the simulations, and they were provided by people at the LCLS in Stanford. And so you see that, you know, the dispersion is not too high, so you see this is charge dynamics around a given functional group of a para-aminophenol molecule. And then you see that the dispersion is rather low. So the good news is that, in principle, this can also be done by using this XUV pump, XUV probe, attosecond scheme. Okay, another direction. If there is a chemist in the audience, would say, yeah, but chemistry is not about ions. I mean, we like doing chemistry with neutral molecules. I mean, when I perform an experiment in a chemistry lab, I take a product here from a bottle, I put it in a solvent, I put another thing, and I produce a reaction. But these are neutral systems. Is there any way to do something in neutral molecules with the necessary time resolution? These are not only in chemistry labs, but in nature. You know, nature, I mean, nature doesn't ionize. If nature ionized, then we would not be here, you know, for sure. So the light that comes from sun doesn't ionize, unless, you know, the ozone hole grows and then we get ultraviolet light and then we have a problem. But, okay, so the way to do it would be to replace the pump pulse by the shortest pulse you could produce in the visible and the ultraviolet wavelength regimes. What is the shortest one you can produce? Well, for this you have to say to know how large the period of this. I mean, you reduce the frequency of your light, then you increase the period. And what is the period of visible light? Well, the period of visible light is around 2 femtoseconds, a little bit less than 2 femtoseconds. So you cannot produce pulses shorter than 2 femtoseconds, because otherwise you wouldn't have light. You would have something else, but not light. By the way, it's a very interesting topic, research topic to consider, sub-cycle pulses, but this is a completely different field. So one can expect to generate pulses in the UV and in the visible of 2-3 femtoseconds duration to induce these dynamics in neutral molecules. This will not ionize the molecule, and then to take the pictures at different times with an attosecond pulse. I mean, this attosecond pulse will ionize, but it doesn't matter. I mean, the electrons that will escape will carry the image of what happened before. So it's just the way you take the picture. So the only problem is to synchronize these two things, because, well, in the previous pump probe schemes I showed you, synchronization was rather easy, in the sense that, remember, if I was using an infrared probe pulse, since this infrared was the same pulse I used to generate the attosecond pulse through high harmonic generation, they are in the same place, and so I have control on both of them. But if this comes from a different laser, then I have a problem. Well, anyway, these problems are going to be solved, I hope, because this is the topic of the Tomato project, which is precisely looking for producing these ultra-short, visible, and ultraviolet pulses of 2-3 femtoseconds duration that will not ionize any molecule, and therefore will allow us to do chemistry in neutral molecules. And of course, to do that, you need a team, and this team is, you need experts, experimental experts in producing attosecond pulses, but you need chemists as well, and real ones, the ones that produce molecules in the lab and tell you, please don't use phenylalanine. As I was told when I met this guy, this is the most boring molecule you can have to do chemistry. Okay, just in case. So chemists are useful for these things, very useful. Now, final thing I want to say, I have a couple of minutes. Or final, no, before last final. Okay, are we really seeing electrons in motion, or I'm cheating you? Because I'm cheating you a little bit, not only me, but everybody, in the sense that, okay, they say, oh, we observed this. No, no, no. This is what comes from our calculations. What the experimentalists see is this. And this is not this. I mean, you try to reconcile this with this by using some reconstruction procedures, but you don't see the electrons in motion, really. Is there any way to see electrons, the electron density? Yes, this is well known. In condensed matter physics, you have scanning tunneling microscopes that allow you to see, for instance, the HOMO and the LUMO orbitals or any other orbitals of molecules deposited on surfaces. You have the necessary spatial resolution, and you also have, low temperature to avoid that these molecules do not move. And this is just an example I took from my own research, in the institute where I work, but there are thousands of examples like this. So, and here you see this is this molecule, which is TCNQ, and you can see, in the experiment, these nice features, which are nothing else than the HOMO and LUMO orbitals of this molecule when they are deposited on a graphene substrate. Okay, so this is. Now, the problem of STM, of scanning tunneling microscopy, is that this technique does not have attosecond resolution at all, of course. It's very far away from having attosecond resolution. So, the idea that was implemented in a recent work in which I was involved, and is to combine what we know in attosecond science with scanning tunneling microscopy. It is to use an STM to take an image of the electron density of your molecule at different delays between the pump and the probe pulses. And this is a setup, an experimental setup that has been built in Stuttgart, in the Max Planck Institute in Stuttgart, and well, I'm happy to say that one of the experimentalists who built this machine is here, sitting in the second row. Okay, so basically what they did is they took this PTCDA molecule, which is, this monster over here. And then, by using this pump probe scenario, they produce a wave packet that involved the HOMO and the LUMO, and then by varying the time delay between the two pulses, they generated some electron motion. And these are two pictures they took with their STM at different delays between the pump and the probe, where you can see that sometimes the electron density is concentrated outside the ellipses, sometimes it's located inside the ellipses, as here, for instance. Okay, so you see that depending on when you are looking at this, you see that the charge is evolving from one side to the other one. And this is the movie they got. Of course, the resolution is not as nice as the one I showed you for the HOMO and LUMO orbitals of the other molecule, but take into account that it's not trivial at all to combine STM with two lasers, synchronized lasers, with the necessary attosecond resolution. But it shows that they are able to do that. And well, I cannot refrain myself from showing the theoretical movie that we calculate, which of course is much nicer because we have all the resolution we want, but basically shows the same thing, how the density moves from one side to the other one. And this is very nice, because if this technique extends or is improved, this will simplify the life of theoreticians, Eva, very much. We don't need to include nuclear motion. We don't need to include the effect of the probe pulse. We don't have to include any nuclear motion or dissociation or whatever. That's great. Our lives will be much, much simpler. So I'm confident that this field will progress. So conclusions. Well, there are many conclusions, but I think these two are probably the most important ones, is that just to tell you that XUV and X-ray light pulses of attosecond duration now are in place, and they can be used to investigate electron dynamics in real time, that when combined with theoretical simulations can give you an almost complete picture of what is going on. And for this, you need supercomputers as the ones I showed you. And don't forget that the essence of chemistry, but also of elementary processes in biology and other is precisely electronic motion. I mean, in chemistry, we are used to hear that, chemistry is about nuclei. The nuclei separate or come together. Yes, of course. But people usually forget that they do that because the electrons told the nuclei to do it. So if you have the power to manipulate electronic motion, then you can do new chemistry. And I want to show something, because after this long talk, you may think, oh, this attosecond business is really great, super new, super modern, super whatever. Well, there was a time in which we didn't know we were doing attosecond science. And here I took two examples. One from myself, when I was a PhD student, and one from, I think he's not here because he's the vice rector of the university, is Henrik Sederqvist here. From about the same time, I don't know if he was his PhD or his postdoc, something like that. Anyway, these are collisions, atom-ion molecule collisions, performed at rather high energy, let's say typically kilo electron volts per atomic mass unit, or even mega electron volts per atomic mass units. And when you have a collision like this, the interaction time between the projectile and the target is of the order of attoseconds. So you are inducing electron motion in the attosecond time scale, but in those days nobody called this attosecond science. So, but the physics behind this, and many of the tools that we use, come from this. And they were well ahead about attosecond science as we understand it today, in the sense that they were indeed able to induce chemical reactions, not in hydrogen or in phenylalanine, in monsters like these ones, clusters of fullerenes, by producing new bonds, okay? Simply because they were inducing electron dynamics, special electron dynamics in the necessary time scale to manipulate the system. And this is just an example of one of the collaborations we have. So we have here Henning and many others. So it was a long time ago, I should say. But okay, so you want to know more? I invite you to read this chemical review paper, where you can find all the history of attosecond science since the first attosecond pulses were synthesized, not the prehistory I showed you before. And if you know Spanish, you can read this. This is very nice for students, undergraduate students. It's written in Spanish. It's Scientific American, but it's the Spanish version, so maybe there is a translation into English. And of course, I cannot forget all the people who were involved in these things along the years. There is a list of the people, students, postdocs. As you can see, many of them left the group and are doing other things. And also long-term collaborators in this attosecond science business. And of course, I want to acknowledge all the funding agencies that have supported this research along all these years. And thank you very much for your attention.
Thank you very much. So we have time for questions.
Yeah, probably, yeah.
I'll speak down maybe. So I'm a novice at this, and I don't know the field very well, but when I think of this, you always talk about it in the time domain, as analyzing individual pulse interacting with the molecule. But if I think of it in the frequency domain, I mean, really you have this pulse train coming out of your laser. And in the frequency domain, that's a comb, a discrete.
Yes.
And then I would ask how these lines of this comb overlap with the lines of the atom. Would you have processes where you have excitations involving multiple pulses?
Yeah, this is there was a big gap in my presentation. You're right. What comes from high harmonic generation is a train of attosecond pulses, so you have a comb, a frequency comb, with discrete frequencies. But what these people do is to isolate one of these attosecond pulses. So they don't have a frequency comb anymore. They have a broad distribution of frequencies, continuous distribution of frequencies. But Yeah, but there are experiments more primitive than these ones in which they use directly what they call the attosecond pulse train, which is the frequency comb, and of course you have these complications that you mentioned, and these are much more difficult to interpret, except for one thing, which is the rabbit thing. But rabbit is reconstruction of attosecond beatings by interference of two photon transitions. This is a technique that is nowadays used, which is extremely useful to measure ionization times, but only that. So if you want to see what happens in the molecule after you induce some dynamics, this doesn't work. So knowing the ionization times is in itself a very challenging problem already in molecules, not in atoms, as you know. Well, maybe in atoms, but there are always more complicated atoms where you can find interesting phenomena. But I would say in molecules, by far, this is much more complicated because the presence of the nuclear motion. And so even this little problem of estimating how long an electron takes to escape from the molecule is complicated. And rabbit for this, using the attosecond pulse train directly instead of a single attosecond, is something that brings a lot of information and has the advantage that you have several pulses, so you have better signals, everything, the experiments are cleaner, etc., etc.
Now we have it on, I think. Do we have some more questions? Yeah, Richard.
So I got a question. So I was thinking about the last topic you talked about, where you put the molecule on the surface, and then you use the electron microscopy to look at what the electron is. I guess there must be a huge interest in this in the role of, let's say, catalysis, where you use the surface itself to change the electronic energy levels of the molecule that's on the surface.
Could you repeat the last part of the question? Because
You change the electronic energy levels of the molecule by putting it on the surface. So there's the
yeah, of course. I mean, it depends on the surface. In this particular example, that is a proof of principle experiment, of course, you have gold, I didn't say it. And, well, gold is rather inert, but you are right. I mean, the position of the home, the LUMO, of the molecules changes by putting the molecule there. But if you put, instead of gold, on top of gold, you put layers of, let's say, sodium chloride, which is an insulator. I mean, you put a few layers of that. It's something that STM people can do currently. Then you would not have this effect. So you would have the HOMOs and the LUMOs and the molecular orbitals almost intact, as they are if the molecules were isolated in vacuum.
Sure, but then you could also investigate the role of the surface. Like
Yeah, sure.
vanadium oxide as a catalyst.
Of course, and in fact, well, I didn't show it, but it's in the paper. This is the example I wanted to show because it only involved motion between the HOMO and the LUMO. But there is another example in the paper in which, by using a different distribution, I mean, this is one monolayer, but the experimental result I showed was for the case of 4 monolayers of PCTDA, so that we could follow the dynamics generated in the upper monolayer that is far away from gold, and it only involves the molecules. But they also perform an experiment for a single monolayer, and in that case, you also have a surface state there that lying between the HOMO and the LUMO, and these surface states contribute to the dynamics. So it's a very interesting dynamics in the sense that it involves both the molecule and the surface. And but I didn't say anything about it, but it's in the paper.
Yes.
Could you imagine to apply electric fields to those surfaces to see field emission, the electron field emission?
Well, I think this is a question more for an experimentalist and theoretician. I don't know what to answer. Maybe if I answer this, I would say nonsense. Why not? I would say in principle, why not? But I probably am not the right person to answer this question. I don't know.
Okay. Do we have some more questions?
The students should ask questions.
Yeah.
I mean, they had the training this morning. So I think I was hoping to have some.
Could you go to slide
38.
Yes. And so there's an interesting expression detailing the color bar on the plot that is shown.
This one.
Yeah, exactly. So
Yeah.
if I understand correctly, the data that the color bar is showing, that is the output on some complicated quantum mechanics made by a supercomputer.
No, this comes from a real measurement. In fact, this comes from a rabbit experiment. But I could not cover all these things in 50 minutes. So it comes precisely from the scenario you described, okay? And which is about measuring ionization times. And so that's why we see the birth of the wave packet, because it allows us to get information during the time the electron is being produced. Okay? Now, what is plotted here, I mean, this comes from measurements, real measurements, photoelectron spectra, with a high energy resolution, high temporal resolution. And then what they are able is to, again, this is explained in the paper at length, but here they plot, this is the photoelectron energy, at different delays between the attosecond pulse train and the infrared probe pulse. And this is what they get. And so what I show here is, are cuts in the right-hand side here. I showed different cuts at different times, and then you see how this wave packet builds up. So you see that there's nothing here before you come with your attosecond pulse train. Then suddenly you start seeing electrons, okay? And you see that the electrons that are produced, I mean, the energy of these electrons changes with time. And this is just the Fourier transform of your electronic wave packet.
But the color coding is the...
And the color code, the orange bar shows, I'm just...
but the green color code, that is the number of electrons.
Exactly. The number of electrons that you get in your detector. So this is not theory. This is experiment. Now, I didn't show theory, because if I show theory, I would show exactly the same figure. The agreement is perfect. But this is helium. I mean, for a theoretician, at least helium, we should know how to do it. But it's identical. But this comes directly from experiment. It's not like this nice movie in phenylalanine with nice color. This comes only from theory.
Okay. I see no further hands, so thanks a lot for coming, and thanks a lot for the talk.
Thank you.